Dr. K. Sendilkumar, Assistant Professor, Department of Physics, Loganatha Narayanaswamy Government College, Ponneri, Chennai. He has done PhD in Material Science at Anna University, Chennai. He has 17 years of teaching experience. He has published 5 articles in national and international conferences and journals. He attended more than 14 conferences and workshops in all over India.
Welcome to UGC lecture series. Today we are going to see the subject quantum mechanics. In this subject we have been seeing so many topics. Now in this session we are going to see particularly about electron probability density, angular variation of probability density, radiative transitions, then selection rules. Electron probability density. We know that density means number, how many number, that is numbers per unit volume. Electron density means number of electrons present in a particular volume, that is electron density. So, electron probability density means what are the probability available where the electrons present in a particular volume, that is electron probability density. That means there is no definite orbits in which now all the electrons are occupied. So, based on this scenario we are going to explain about electron probability density. We know that in Bohr's model of hydrogen atom, the electron is visualized as revolving around the nucleus in a circular path. So, this model is pictured in a spherical polar coordinate system. We know that we are already familiar with spherical polar coordinate system, that is we have been seeing from quantum theory of hydrogen atom, and in the last session we have seen the spherical polar coordinates in quantum numbers also. It implies that if a suitable experiment were performed, the electron would always be found a distance of r is equal to n squared a naught. We know that we have seen n is the principal quantum number, then a naught is the radius of the orbit from the nucleus. So, this equatorial plane theta is equal to 90 degree, while its azimuth angle pi changes with time. The quantum theory of hydrogen atom modifies the Bohr model in 2 ways. That means no definite values of r, theta, phi, these are all the spherical coordinates, can be given, but only the relative probabilities for finding the electron at various locations. The probability density that corresponds to the electron wave function. So, what we have seen, that is the psi is the wave function of the hydrogen atom, that is wave function of the electron present in the hydrogen atom in terms of r, theta, phi. So, r, theta, phi is a function of small r, capital R, and small theta, capital theta, small phi, capital phi. So, this r represents r of r, theta of theta, phi of phi in the hydrogen atom. Modulus psi squared is equal to modulus r squared, modulus theta squared, modulus phi squared. This is equation number 1. As usual, the square of any function that is complex is to be replaced by the product of the function and its complex conjugate. So, we know that we always use complex conjugate, that is complex conjugate means we are already familiar with this. So, that is imaginary part should be negative. So, we see that azimuthal angle phi. So, based on azimuthal angle we have got a solution that also we have seen in the previous session, that is phi of phi is equal to a into e power I ml phi. The azimuthal probability density, that is if we say the function phi, then the probability density means modulus phi squared. So, modulus phi squared can be written as, that is modulus phi squared is equal to phi star into phi. So, this phi star is the complex conjugate of this phi, and its value is a squared e power minus I ml phi, e power I ml phi, we get e power 0 because this is negative term, this is positive term. So, together we will have 0. So, we know that anything power 0 is equal to 1. So, a squared into e power naught is equal to a squared. Now, let us see the probability of finding the electron. So, previously what we have seen, electron probability density, that means the probability of density of electron where it is present inside the orbits. Now, we will have to find where the electron is. So, that probability we are going to see. So, that is the probability of finding the electron in the orbits, say for example, s orbit, p orbit, d orbit, like that. So, the probability density of the electron at the point r theta phi is proportional to then our modulus value, that is wave function we all know that represented by psi. So, this spherical polar coordinate r theta phi is proportional to this modulus psi squared. We know psi is a wave function, but the actual probability of finding it in the infinitesimal volume element dV, then it is written as modulus psi squared into dV. dV is the small elemental volume. So, that volume element we can write. So, volume element dV is equal to dr into r d theta r sin theta d phi. So, we simplify r squared sin theta dr d theta d phi. This is equation number 2. So, x axis, y axis, z axis, 3-dimensional space we can draw a sphere. So, one with the radius r, another with the radius r plus dr. So, what is this shape? This shape is one actant of the sphere will be like this, one actant of the sphere. So, I can easily explain what is meant by one actant of the sphere. You take an apple, cut into 8 equal pieces. So, one of the piece will be shaped like this. So, this we will have this. So, in this region, say this is r plus dr. In between this region, if we consider a small elemental volume, that volume equation the volume value is dV is equal to r squared sin theta dr d theta d phi, as theta and phi are normalized functions. The actual probability P of r dr of finding the electron in a hydrogen atom somewhere in the spherical shell between r and r plus dr from the nucleus. We know nucleus is a spherical one. So, in the sphere, if we consider a region between r and r plus dr, then where it is placed. So, what is the probability of finding the electrons within this region, say on r and r plus dr, that we are going to see here. So, the probability of finding the electron, we can write the equation, that is P of r dr is equal to r squared into modulus r squared dr integral 0 to pi modulus theta squared sin theta d theta into integral 0 to 2 phi modulus phi squared d phi, that is phi varies from 0 to 2 pi, then theta varies from 0 to phi. So, on simplifying this equation 3, what we are getting? R squared modulus r squared into dr. So, the probability of finding the electron in a hydrogen atom in the spherical shell between r and r plus dr from the nucleus, we can see this diagram. So, from this diagram we can clarify this. So, this is nucleus. We know that nucleus is in spherical shape. So, this portion is called one actant of the sphere. One actant means 1/8 of this total spherical volume. So, in which up to this is radius of the sphere is r, after this is radius of the sphere is r plus dr. So, this is r plus dr. So, in between this region, how many electrons are present? What is the probability of finding the electrons in this region r and r plus dr? That is what we are going to see in this topic. So, the probability of finding the electron in a hydrogen atoms at a distance r and r plus dr from the nucleus for quantum states. See this picture. Small r represents radius of the orbit from the nucleus. P of r dr represents the probability of finding the electron in between the region r and r plus dr. So, we have got the electronic states for this graph. So, 1s, 2s, 3s, 2p, 3p and 3d. So, this is electronic configuration. We used to sequentially say 1s, 2s, 2p, 3s, 3p, 3d. This is the sequence to read the electronic configuration. Now, let us see the angular variation of probability density. Angular variation. So, probability density, what we have seen? Electron density present in the orbit. So, how this electron probability density varies in terms of angle, that is the angular variation of probability density. The function theta varies with the zenith angle. So, as we have seen earlier in spherical polar coordinates, r represents position vector, theta represents zenith angle, phi represents azimuth angle. So, this zenith angle theta varies with the function angle theta. So, capital theta of small theta we have considered in separation variables. Accordingly, we are dealing this topic. For all quantum numbers L and ML except L is equal to ML is equal to 0, which are all the states. So, the values of modulus theta squared for an S state is constant, that is the value half. That means, the value of this zenith angle, that is a normal value modulus squared for an S state, S is an orbit in which the electrons are present. So, we call electronic energy states of S orbit, we call it as S state, is constant and value is half. This means that since modulus phi squared is also a constant, the electron probability density modulus psi squared is spherically symmetric. It has the same value at a given r in all directions. Electron in other states, however, do have angular preferences, sometimes quite complicated ones. Since modulus psi squared is independent of phi, we can obtain 3-dimensional picture by rotating a particular representation about a vertical axis. Now, we will see the radiative transitions. What is meant by radiative transitions? What is meant by transitions? So, consider this is lower energy, say E naught, this is higher energy, say E1. When atom or ion de-excite, if it emits any emission, that is called radiative transition. We know that you might have been studied in the laser topics. So, ground states and excited states we know. If the atom or molecule or ion moves from lower energy state to higher energy state, that we call it as a de-excitation. Vice versa, if the atom, the same atom from higher energy state to lower energy state, that is called a de-excitation. So, during this de-excitation, if it emits any light radiation, that is called radiative transition. If it does not emit any kind of radiation, that we call it as a non-radiative transition. So, according to this principle, we are going to see what is radiative transition quantum mechanically. So, we will see what happens when electron goes from one state to another state, here higher energy state to lower energy state. So, in formulating Bohr's theory of hydrogen atom, Bohr was obliged to postulate that the frequency nu of the radiation emitted by an atom dropping from energy level Em to the lower energy level En. So, the difference of energy, here we will have a frequency of the radiation emitted during the de-excitation. So, we have got a equation for that. Nu is the frequency of the radiation coming out because of the de-excitation. So, Em minus En divided by H, that is higher energy state, energy of the higher energy state, energy of the lower energy state dividing by H, where H is called Planck's constant. It is not hard to show that this relationship arises naturally in quantum mechanics. For simplicity, we shall consider a system in which an electron moves only in the x direction. We know that the time dependent wave function psi n of an electron in a state of quantum number n and the energy level En is the product of time independent wave function psi n and time varying frequency nu n. So, nu n is equal to En by h. We are familiar, E is equal to h nu is a Planck's equation. From this only we have got this equation, nu n is equal to En by h. So, hence psi n is equal to psi n of e power minus I e by h cross into t. So, this equation we have seen already in the time dependent Schrodinger wave equation. So, the complex conjugate of this, so we have to just change this imaginary term, minus becomes plus here. So, this altogether we will write as equation number 1. So, the expectation value of the position of such an electron is expectation x is equal to integral minus infinity to plus infinity x psi n star psi n dx is equal to integral minus infinity to plus infinity x psi n star psi n e power I e n by h cross minus I e n by h cross into t dx. So, on simplifying we get integral minus infinity to plus infinity x psi n star psi n dx. This is equation number 2. We conclude that at some time during the intervening period the system excited in the state m, that the wave function of electron that can exist in both state n and ms, that is psi is equal to a psi n plus b psi m, because n represent the ground state energy, m represent excited state energy, where a star a is a probability that the electron is in state n and b star b is the probability that is in the state m. Of course, it must be always be true that a star a plus b star b is equal to 1. So, a star a plus b star b is equal to 1. A star is a complex conjugate of a, b star is a complex conjugate of b. So, together if we sum up the resultant value is 1. Initially a is equal to 1 and b is equal to 0. When the electron is in the excited state, a is equal to 0 and b is equal to 1, and ultimately a is equal to 1 and b is equal to 0 once more. While the electron is in either state, there is no radiation, but when it is in the midst of the transition from m to n, electromagnetic waves are produced. So, that is why we used to say this is called radiative transition. That means, when the electrons moves from higher energy state to lower energy state, there will be electromagnetic emission during the de-excitation process. That is why we term it as radiative transitions. So, this we can see quantitatively. The expectation value corresponds to the composite wave function, that is expectation x equal to integral minus infinity plus infinity x into a star psi n star plus b star psi m star into a psi n plus b psi m dx, that is integral minus infinity plus infinity x into a square psi n star psi n plus b star a psi m star psi n plus a star b psi n star psi m plus b square psi m star psi m dx. This is equation number 4. Here, as before, we let a star a is equal to a square, then b star b is equal to b square. We take this into account in our case. So, the expectation value can be rewritten as expectation x is equal to a squared integral minus infinity to plus infinity x psi n star psi n dx plus b star a integral minus infinity plus infinity x psi m star e power plus I e m by h cross into t psi n e power minus I e n by h cross into t dx plus a star b into integral minus infinity to plus infinity x psi n star e power plus IEN by h cross t, then psi m into e power minus IEM by h cross t dx, plus b squared integral minus infinity to plus infinity x psi m star psi m dx. This is equation number 5. Because we know that e power I theta is equal to cos theta plus I sin theta, then e power minus I theta is equal to cos theta minus I sin theta. So, the middle of the equation, that is what we have seen in the previous equation, which are functions of time, that becomes, so cos of Em minus En by h cross into t is multiplied with integral minus infinity to plus infinity x b star a psi m star psi n plus a star b psi n star psi m dx, plus I sin Em minus En by h cross into t integral minus infinity to plus infinity x into b star a psi m star psi n minus a star b psi n star psi m dx. This is equation number 6. So, the real part of this result varies with time, as so cos of this value Em minus En by h cross into t is equal to cos 2 pi Em minus En by h into t, that becomes cos 2 pi nu t, because this value is nu, what we have seen in the first slide. So, the electron's position therefore oscillates sinusoidally at the frequency. So, nu is equal to Em minus En by h. This is equation number 8. When the electron is in state n or state m, the expectation value of electron position is constant. When the electron is undergoing a transition between these states, its position oscillates with the frequency nu. Such an electron, of course, is like an electric dipole. Electric dipole means two poles. So, the distance between positive pole and negative pole, we call it as a dipole, that is a electric dipole. So, electric dipole and radiates electromagnetic waves of the same frequency nu. So, this result is the same as that of postulated by Bohr and verified by experiment. Next we will see selection rules. So, what are the rules for this radiative transitions? That is, what are the transitions are allowed, what are the transitions are forbidden. So, some transitions are more likely to occur than others. So, we did not have to know the values of the probabilities A and B as a function of time, nor the electron wave function psi n and psi m in order to find the frequency nu. We need these quantities to calculate the chance of a given transition will occur. The general condition necessary for an atom in an excited state to radiate is that the integral not to be 0, since the intensity of the radiation is proportional to it. So, integral minus infinity to plus infinity x into psi n into psi m star dx. So, transition for which the integral is finite are called allowed transitions, while those for which it is 0 are called forbidden transitions. We know we have seen energy level diagrams in electronics, particularly some energy band diagrams, that is, we know forbidden bands as well as allowed bands. So, allowed bands are called, we used to say energy gap, forbidden bands are we used to say forbidden gap. So, the same principle we are adopting here also, but it is quantum mechanically. So, in this case the hydrogen atom will be having 3 quantum numbers are needed to specify initially, and final states involved in a radiative transitions. If the principal, orbital and magnetic quantum numbers of in the initial state, let it be n dash, l dash, ml dash, that is initially principal quantum number, orbital quantum number, magnetic quantum number. This is initial electronic energy level. Then in the final electron energy level, and it becomes n dash becomes n, l dash becomes l, ml dash becomes ml, and u represents either the x, y or z coordinate. The condition for allowed transitions: integral minus infinity to plus infinity u into psi n l ml psi star n dash l dash ml dash dv is not equal to 0. So, if integral is not equal to 0, that is called allowed transitions, where the integral is now overall space. When u is taken as x, for example, the radiation would be produced by the dipole antenna lying on the x axis. Since the wave function for the hydrogen atom are known, then what we have seen, the equation 2 can be evaluated for u is equal to x and u is equal to y, then finally u is equal to z for all pairs of states differing in one or more quantum numbers. When this is done, it is found that the only transition between states of different n that can occur are those in which by the orbital number L. So, orbital number L changes by +1 to -1 and the magnetic quantum number ML does not change or changes by +1 to -1. So, there will be a difference between this orbital quantum number L and magnetic quantum number ML. So, now let us see the conditions. The condition for an allowed transition is that del L is equal to +or-1. So, this is for allowed transition. So, delta L is equal to +or-1. Then selection rules represents delta ML. Delta L means the variation in the orbital quantum number. Delta ML means the variation in the magnetic quantum number. So, this varies from 0, ±1. So, the change in the total quantum number n is not restricted. So, the above equation what we have seen 3 and 4 are known as the selection rules for allowed transitions. See here, this is the lower energy state, this is the excited energy state. So, these are all the transitions. So, this L is equal to 0, 1, 2, 3 represents orbital quantum numbers. This n is equal to 1, 2, 3, 4 etc. up to infinity is a principal quantum number up to the higher energy state. So, n is equal to infinity. When there is a transition, the transition means the electrons travels from higher energy state to lower energy state. Similarly, in all energy state we will have a transition. See, this is one transition, this is another transition, this is transition. During these transition, if there is any emission of light from this, so this is called de-excitation, higher energies to lower energy state. Then if there is emission, that is called radiative transition. For this, what is the allowed transition band, what is the selection rules, that is what we have seen in this topic. So, now let us summarize what are the topics we have seen in this session. So, we have seen electron probability density, in which we found where the electron is exactly located in between r and r plus dr in one octant of the sphere, what we have considered in the spherical nucleus, in which we also have seen angular variation of probability density. Then we have seen radiative transition, what are the de-excitation, then what are the electromagnetic emission during the de-excitation. Then we have seen selection rules, what is the forbidden band, what is the allowed band, what are the rules for those forbidden and allowed transitions. Now, let us see the questions in this involved in this session. Under what circumstances is an atomic's electron's probability density distribution spherically symmetric? Why? And the second question, find the most probable value of R for a 3D electron in a hydrogen atom. Then the third question is, how much more likely is the electron in a ground state hydrogen atom to be at the distance a0 from the nucleus than at the distance 2a0. The rest of the topics we will see in the next session. Thank you.